right, guys, today we're going to do a quick review of integration by parts and then look at how we can extend this just one little step further. So on your homework yesterday, you had a problem similar to this. I believe this is actually question number 4 on last night's homework, where you wanted to use integration by parts to evaluate the integral of the inverse sine of x dx. Now, we don't have a rule for the inverse sine of x dx, so we're going to use that integration by parts strategy where we break up the integral into 2 parts. Remember, what we're trying to do as we break it up is we define one part as u and one part as dv. And we want to choose a u so that u is something we can easily find the derivative of, and we want dv to be the part that's easy to find the antiderivative of. So in this case, since we don't know the antiderivative of the inverse sine of x, that's going to be our u. And we do have our derivative rules for the inverse sine. And our dv is just going to be that dx part. Now, once we identify our u and our dv, we're going to differentiate the u and we're going to anti-differentiate the dv so that we can get the pieces we need for our integration by parts formula. So we need uv minus the integral of v du. So u is going to be the derivative of the inverse of sine. So that's just going to be 1 over the square root of 1 minus x squared dx for our du. And then if dv is equal to dx, then v, our antiderivative, is just equal to x. So now that we have our pieces, we can go ahead and put them into our formula for the integration by parts. So we're going to go ahead and take u times v, so the inverse sine of x times x. I'm going to put the x first, just so that it doesn't look like that x is inside the extra x is inside there. So I'm taking u times v, so I did x times the inverse sine of x, minus the integral of v, which was x, and then du, which is this 1 over the square root of 1 minus x squared dx. Now, as we're building this, we want to make sure that this is an integral that we can actually anti-differentiate. And in order to anti-differentiate this piece, we're going to need to use our substitution technique because we don't have any rule right now that's going to anti-differentiate this quantity. So when I have a function like this, I'm going to let u represent that inside piece. I'm going to switch to a different marker to show that I'm using a different u. So over here, I'm going to use u substitution to evaluate this integral. So I'm going to let u equal that 1 minus x squared. Then du would be negative 2x dx. And then I'm going to solve for that dx, and I'm going to find out that du over negative 2x is equal to dx. So I can use this now to go and replace into this integral so that I can use the u substitution to work that out. So this is going to stay x times the inverse sine of x minus the x that's already there times 1 over the square root of u. And I'm going to replace this dx now with this value right there. So I'm going to replace that with the du over the negative 2x. Now what's going to happen is this x and that x are going to cancel. So I'm going to be left with x times the inverse sine of x minus, let's pull that out actually. So let's see, negative, and that's at the bottom. So positive 1/2 times the integral of 1 over the square root of u du. We can rewrite this as u to the negative 1/2. So we're going to get x times the inverse sine of x plus 1/2 the integral of u to the negative 1/2 du. And we can now find that antiderivative. So we would get x inverse sine of x plus 1/2. We're going to add 1 to that exponent. So that would become u to the positive 1/2, and then we multiply by the reciprocal. We're done anti-differentiating, so we're going to take care of our plus c. And then to finish up the problem, I'm just going to go ahead and replace u with the value that I found from this piece, because remember, this u was from my antiderivative of this. So not this u right here. You could call them u1 and u2, but I think as long as you know, once you've gone past this step, and we define this u over here, we don't need to worry about separating them. So I think we're okay with that. So we're going to finish up the problem. And 1/2 times 2 is just 1. Instead of u to the 1/2, I'm going to get that 1 minus x squared to the 1/2 plus c. And of course, you could write that if you really wanted to as x times the inverse sine of x plus the square root of 1 minus x squared plus c. And that would be our integration by parts technique for this problem, kind of attaching on a secondary substitution step. Now, sometimes as we're going through the integration by parts technique, you might go ahead and create a new integral that is simpler than what you started with, but yet you're not able to anti-differentiate. So sometimes you might need to use what we call a double dipper type of technique, where you don't just do integration by parts one time, you actually have to do it 2 times. So this right here is going to be an example of our double dipper type of problem. When I try to go and look at this, I can't use u substitution like we did over here to try to clean up the integral, because if I let u equal e to the x, it's just going to stay e to the x, and it's not going to clean up the x squared. And if I let u equals x squared, that derivative is going to become 2x, and it's not going to help me clean up that e to the x. So in this case, since I don't have a rule for this, I'm going to use that integration by parts technique. So again, I'm going to need to break this up, and I'm going to need to identify a u and a dv from that. And again, I want my u to be something I can easily differentiate, and I want my dv to be something that I could easily anti-differentiate. So if I were to let dv be the x squared piece, when I anti-differentiate, I'm creating an x cubed, and I'm not really making my life any better by raising that to an x to the 3rd power. So for this problem, I'm going to let u equal the x squared, because I could easily differentiate that and find out that du would be equal to 2x dx. And I'm going to let the dv be the remaining part of it. I'm going to let that be the e to the x dx. And that way, when I go to take my antiderivative, we know the antiderivative of e to the x is just e to the x. So if I drop this now into my integration by parts formula, I'm going to take u times v, so x squared e to the x, minus the integral of v du. So e to the x times 2x dx. Now I should be always looking at this and figuring out, did I make this integral easier to work with than the original problem? And it seems like I'm heading in the right direction, right? Because 2x is obviously better than x squared. I still have the e to the x there, but unfortunately, I still don't have a rule or a way to anti-differentiate this. So I'm just going to pull that 2 out and rewrite this a little bit neater. So I kind of have this scenario going on. And again, I want to go through the process, and I don't have a rule. And again, substitution is not going to work for me, because if I let u equal e to the x and try to use u substitution, I'm not going to be able to get rid of that x. And if I let u equal the x, I'm not going to be able to get rid of e to the x. So this is a double dipper type of scenario. I want to go ahead now and use integration by parts again, but now for this piece. So as I go to try to find the integration by parts for this piece, I'm going to create another scenario where I'm finding these same 4 pieces, but now using this integral. So for this one right here, again, I want to find a u and a dv. You could define new variables if you want, but I just like to use the same formula over. So I'm going to switch it over to the purple pen. Not that I really think it's going to make a big difference, but for this guy right here, I want to find a u and a dv for this integral. Again, the e to the x dx is going to be the part that's easier to anti-differentiate. So I'm going to let dv be the e to the x dx, so that would make v e to the x. And I'm going to let u equal x, and the derivative of that would be just 1 dx. Now, as I go to do the double dipper part, I'm really evaluating this full integral. So all of the stuff that I found so far is going to come along for the ride. So this x squared e to the x is going to stay. That minus 2 is going to stay. But now I'm going to apply the integration by parts to this new integral. I'm replacing this now with the integration by parts formula. So I'm going to take this integral and replace this now in this brackets here with the uv. So the x e to the x minus the integral of v du, which is now just e to the x dx. And as I look at this now, I can definitely see that this new integral is a lot easier to work with. And actually, we know how to anti-differentiate e to the x. So all of our hard work has paid off. It just took us 2 rounds of integration by parts to get here. To finish up, I'm just going to go ahead and simplify what I have here. So x squared e to the x is going to stay. I'm going to distribute that -2 into there, so minus 2x e to the x. I'm going to distribute the -2 in here. A -2 times that negative is going to give me a +2. The antiderivative of e to the x is e to the x. And since I'm at the end of my integral, I'm going to put my plus c. So my final answer for this would be this long chain of values, starting with my original integration by parts, and then doing a double dipper technique where I defined another set of u and dv values to go ahead and replace in. All right, so you're going to go ahead and practice a couple of these on your own, and if you have any questions, feel free to reach out.